In this exercise, we are given two cylinders 2 and 4 meters in diameter respectively, and so that their central axes intersect at 60 degrees. Our task is to find the volume of the region that is inside both cylinders. It is generally the case that when two cylinders intersect, the curve or curves of intersection will not be circular. This is complicated by the fact that the two cylinders have different diameters and are not perpendicular to each other. We are going to find the volume of the region between these two curves of intersection. We observe that the lateral side of the region lies on the small cylinder while the end faces lie on the big cylinder. To better describe our strategy for finding the volume, we look at the region from a different vantage point. The method that we will use to find the region's volume is called the method of parallel plane sections. As the name suggests, we use parallel planes to slice up the region. We have infinitely many options as to how we can orient the parallel planes. We choose slicing planes that are parallel to the plane determined by the central axes of the two cylinders. Between pairs of parallel slicing planes are slabs that we refer to as sections. These sections have positive thickness. The top and bottom faces of each section are parallelograms, but we should not expect any of the sections to be a parallelepiped or a solid each of whose faces is a parallelogram. In fact, at least one face of each section is curved. On the section shown, two of the faces, one of which we label as f(1), lie on the small cylinder, and another two faces, one of which we label as f(2), lie on the big cylinder. We disregard the curvature of any of the faces, so that we approximate the volume of each section using a parallelepiped. We construct the parallelepiped for each section by dropping 4 faces, one from each edge of the top parallelogram face of the section to the bottom parallelogram face of the section, so that these new faces are perpendicular to the slicing planes. Suppose that we have a total of n sections. Suppose that what we have on screen is the parallelepiped for the ith slice, where I goes from 1 to n. The volume v sub I of the ith parallelepiped is equal to the product of its length. We call this length L sub I. The distance between the two parallel lengths, we call this distance h sub I, and the section's thickness. We call this thickness delta sub I z. We draw the z-axis so that it is perpendicular to the slicing planes. Since we have chosen to express the thickness in terms of z, we must also formulate L sub I and h sub I in terms of z. In order for us to be able to do this, we view the section from above the plane of the central axes and directly above their intersection. We also superimpose the two intersecting cylinders. This side of the top parallelogram face, and which runs along the small cylinder, has length L sub I. Its endpoints are on the big cylinder. This segment, which is perpendicular to L sub I and which runs between two parallel sides of the parallelogram, is the distance h sub I. The endpoints of h sub I are on the small cylinder. From one endpoint of L sub I, we draw a perpendicular to the other side of the big cylinder. We construct this perpendicular so that it is on the same plane as the top parallelogram face of the section. Let the length of this perpendicular be m. Then we have a right triangle with base angle 60 degrees, m as the opposite side, and L sub I as the hypotenuse. If we can find m in terms of z, then we should be able to find L sub I in terms of z by simple trigonometry. Suppose our line of sight is the central axis of the big cylinder, so that we are looking directly through the big cylinder. The black segment will be the segment M, which is coplanar with the section's top face. We draw the z-axis, which is perpendicular to M, so that it passes through the big cylinder's central axis, which is marked by the center of the circular cross-section of the big cylinder. Let z be equal to 0 on the big cylinder's central axis. Suppose that the z value on the top face of the ith section lies on z equals z sub I. The length of this segment must be m over 2. With the radius of the big cylinder at 2 meters, the Pythagorean theorem says that the square of m over 2 plus z sub I squared equals 2 squared. Solving for m, we get m equals 2 times the square root of 4 minus z sub I squared. On the left diagram, m is shown to be opposite the 60-degree base angle of the right triangle. Therefore, m over L sub I equals sine 60 degrees. And sine 60 degrees is the square root of 3 divided by 2. Replacing m by 2 times the square root of 4 minus z sub I squared, we find that L sub I equals 4 divided by the square root of 3 times the square root of 4 minus z sub I squared. To find h sub I in terms of z sub I, this time we'll look straight along the central axis of the small cylinder. This segment is segment h sub I. The z-axis is still perpendicular to the plane of the two central axes with z equal to 0 on this plane. Also, h sub I is at z equals z sub I. The length of this segment must be equal to h sub I over 2. The radius of the small cylinder is 1 meter, so that by the Pythagorean theorem, we have the square of h sub I over 2 plus z sub I squared equals 1 squared. Solving for h sub I, we have h sub I equals 2 times the square root of 1 minus z sub I squared. And so using these formulations of L sub I and h sub I in terms of z sub I, v sub I is equal to 4 divided by the square root of 3 times the square root of 4 minus z sub I squared times 2 times the square root of 1 minus z sub I squared times the thickness, which is delta sub iz. Or that v sub I equals 8 divided by the square root of 3 times the square root of the product of the quantities 4 minus z sub I squared and 1 minus z sub I squared. And to this we multiply delta sub iz. And so for a Riemann sum estimate for the volume of the region, the volume of the region is approximately equal to the sum from I equals 1 to n of 8 divided by the square root of 3 of the square root of the product of the quantities 4 minus z sub I squared and 1 minus z sub I squared. And don't forget delta sub iz. If the maximum thickness of all the sections tends to 0, this Riemann sum should tend to a definite integral. Therefore, the volume of the region is equal to the integral of 8 divided by the square root of 3 times the square root of the product of the quantities 4 minus z squared and 1 minus z squared. The lower limit is z equals minus 1 at the bottom of the small cylinder, and the upper limit is z equals 1 at the top of the small cylinder. This is not an elementary integral, but calculating the value numerically, we find that the volume of the region is 14.04 cubic meters up to 4 significant digits.